Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently doing a postdoc over in the University of Helsinki in the Helsinki Institute of Physics in Helsinki, Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a scientist. I love chatting to everybody about all of the cool things I get to work on. And yeah, for anyone who doesn't yet know, I've messed up my intro. For anyone who doesn't yet know, welcome to Cup of Cosmology. The idea here is that this is an interactive stream. You people can ask me anything you want about space, about physics, about academia, about myself, about cosmology, about my cats. And I will do my best to try to answer your questions. Of course, I don't have all of the answers, but I will do my best to answer the questions that I can potentially answer. If you're a first-time viewer, welcome. If you're a regular, welcome back. If you haven't done so already, like the video, leave a comment, subscribe, do all of the usual YouTube stuff, say hi in the chat. It really does help boost engagement. If you're on Twitch, press all the buttons, make stuff happen. You'll know what to do. You'll know the drill. You know what buttons to press. I see we have a bunch of the regulars coming in here. We have Mito, we have Ben, we have Perth, Sophia, David, Scott, Paul, John. Great to see all of you. Great to see so many regulars and some new people as well, I hope. It's always really nice to see how many of you just tune in every Sunday to hear me chat about random stuff happening inside the universe. Our Cup of Cosmology is in its 10th year now. And I'm still somehow surprised that some of you are still here after 10 years. Some of you are new additions. Some of you have been around since the beginning, back in the Periscope days. And it is really nice to see all of you coming here and chatting and asking me cool things about the universe. So I do not have a topic planned today on account of having an insanely busy week. For the last 2 weeks have been extremely busy for a lot of reasons. So we don't have a topic planned, which means you get to decide what we talk about today. The direction of the stream will depend entirely on your questions. Depending on what you ask, we'll go in one direction or another. So you have creative input into where we take this conversation today. I feel like my camera is a bit messed up. Let me just try and fix this slightly. That might be better. Yes, my camera is slightly messed up because I've gotten in the habit now of, if I'm doing meetings from home, obviously I do them from the same setup. And if my cats are around, I've decided that my colleagues would much rather look at my cats than look at me. So I frequently now move the camera and point it at my cats during work meetings, which now means my camera has gone from being stationary to being a moving thing, which means the angle might have changed a bit. I feel like something's different with the camera, but it's fine. And if a cat does happen to come up here, you will definitely see it. Okay, I see some comments coming in already. Comment from John here. Wants to say thank you for recommending How to Win a Time War. I finished it and it was really great. Never read anything quite like it. I'm glad you liked it. Yeah, it's a very cool book. If anyone here hasn't yet read How to Win a Time War, I highly recommend it. It's got a very creative way of world building and of telling the story, and it really does suck you in a lot. It's a great book. Highly recommend reading that. I'm glad you enjoyed it, John. That is a great book in my opinion. Also, I know of it because it went viral on Twitter a couple of years ago in a really random circumstance, but I'm glad I discovered it because it is a very good book. Okay, let's see. There's another comment here from Scott. I'm going to address the comments and then go to the question that I saw from Paul. Yes, Perth, you can ask questions about white holes. Yes, step away, think about the question. Feel free to ask a question of white hole. I'll start mentally preparing for a question about white holes. Comment from Scott, unrelated to cosmology. I remember you saying learning Finnish was hard, and I just learned last night that Hungarian and Finnish share a common ancestor. Yeah, it's Finnish is a very difficult language for me personally. And I think one of the reasons I struggle with it is because it doesn't share ancestors, or it doesn't have common roots with many other languages. There's only 3 or 4 languages in that family, one of them being Finnish, one of them being Hungarian. Estonian is pretty similar as well for some things. But I speak Germanic languages. I speak English and German. I'm learning Swedish. I speak Latin languages. I speak Catalan and Spanish. I know a bit of French. And they will have very similar grammars and structures. But Finnish is unlike any other European language that I know. And it's one of the reasons I struggle a lot with it. But in just a side note of like personal achievement, I actually managed to have a conversation with a friend in Finnish today. So, small steps, but progress. Okay, let's see. Hey, James, great to see you as well, as always. Great to see all of the regulars coming in. And if you're a newbie here, if it's your first time, do say hello. There's always more people commenting So there's more people watching than people commenting. So I know there's a couple of you who just lurk here, which is fine. You're allowed to lurk. You don't have to comment. But do feel free to say hi in the comments as well. So just occasionally say hi. It's always nice to know who's around. Okay, there's a very interesting question here from Paul. Would you say the most interesting papers or talks have been based on new data or based on new ways to look at old data? That is very, very cool. Matteo, great to see you in the comments. Really nice to see you here. Always nice to see you here, Matteo. Feel free to be as disruptive as usual. If you have difficult questions, go ahead with them. Okay, so this is a very cool question, and then I'll answer about cool stuff in cosmology. So, question from Paul, would you say the most interesting papers or talks have been based on new data or new ways of looking at old data? I would say a mix of both. I think there's a lot of interesting stuff happening right now with new data coming out. We had the first results from DAISY last year, which created a bit of a stir because the DAISY results, the dark energy spectroscopic instrument results, the first preliminary results that they released, seem to indicate that dark energy doesn't behave the way we expected it to behave. So that is pretty interesting. But then there's also there's still a lot of steps needed to be done with this. We still need to figure out why DAISY data looks different to all other data sets that we have concerning dark energy. We need to get more statistics in some range of the data. But the preliminary or first DAISY results released almost a year ago now seem to show that dark energy is changing over time. So the universe has three main components: everything we know, everything we're accustomed to, everything from me to my slightly hyperactive cats to my coffee mug. All of this is normal matter. Normal matter only accounts for 5% of the energy budget of the observable universe. There's another 26.2% in the form of dark matter. This is this weird type of matter that interacts gravitationally, but doesn't interact electromagnetically. And then there's this remaining almost 69%, which is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and we don't know much about dark energy. One of the things we thought we did know about dark energy is that it is constant. Dark energy behaves the same now as it did in the past. However, the first DAISY results seem to indicate that dark energy actually changes throughout cosmic evolution in what is known as time-varying dark energy. And this is very, very exciting, and this was based on new data. But there's still a lot of steps to be done. They're not yet at the stage to claim a discovery with this data. And we're expecting the next data release from DAISY sometime very soon, sometime within the next year, I expect, like this year already, 2025. I forget that we're already in 2025. So that was based on new data. And this is just to give an example, but then there's also a lot of stuff that is still based on old data that people are still trying to unpack. And one big example we can give of this is the cosmic microwave background radiation. This is the oldest light we can see in the universe, less than 10 minutes today for anybody keeping track. This is a snapshot of what the universe looked like 380,000 years after the end of inflation. This map contains the statistical properties or the information of what the universe was up to at this time. So from this map, we can get these precise numbers that I gave you before of like 4.9% normal matter, 26.2% dark matter, and 68.9% dark energy. Those percentages come from the CMB, the cosmic microwave background radiation. So this map, this image here was produced in 2018 by the Planck collaboration. There were previous ones by Planck in 2013, 2015, and even previous ones from other experiments dating back to the early 2000s, or even the late 20th century even. But even though this map is now 7 years old, there is still a lot of ways that people can look at this data. There's some ideas here of have we potentially missed something in terms of the lensing of the CMB? Is there more to be investigated with specific regions that have cold spots or hot spots? So there is still a lot of active analysis and studies being done on this new data. So I think there's a mix. The question was, are there more interesting results coming out from new data or from old data? And I think both, because there's also the idea that if you come up with a new model of cosmology or a new model of dark matter or something different like that, one thing that you're going to do is test this against existing data. So then you're in essence looking at old data. So I think there's an interesting mix in both of these categories of both using new results and revisiting old results. But I also think we shouldn't forget the fact that in cosmology, there's a lot of things that are either very theoretical or very forward-thinking. So by theoretical, I mean papers that come up with new theories or new models that don't necessarily rely on data that we have, or might rely on a combination of new and old data. And these are much more on the model building side. And I think there's a lot of really interesting work being done in those topics as well. To give you an example, what I currently work on is gravitational waves in the very, very, very early universe. So ripples in the fabric of the cosmos produced in the first second after the end of inflation. These are things that theoretically we still don't have as good predictions as we would like. So these are things that, in a sense, rely on future data because we're hoping that we might have the data in the future to study these, but we don't yet have enough predictive power to get the precision that we need for some of these predictions. So, for an example, with these early universe gravitational waves, the way these gravitational waves form, they're still to do the full calculation is computationally expensive. So we often make approximations. And there's a lot of work being done asking the question of how precise do we need these approximations to be? So my point here is that not all cosmology papers rely on either old or current data. Some of them rely on future data. Some of them are just preparing the field so that when we do have future data, we will be ready. You know, not sure if you can hear if my microphone is picking up the fact that my cat is meowing very, very loudly. They're in the middle of zoomies, but yes, if you hear cats meowing, it's because they are full on zoomies mode, and one of them just came running out of the bedroom screaming. But they're fine. They're just playing. They're just playing. Being is slightly disruptive. Yes. So to answer the question, Paul, I think there's a lot of interesting papers about new results. For example, DAISY, the Euclid results that we're going to have at some point this year or next year. There's a lot of interesting papers revisiting old data, and there's a lot of interesting papers doing either theoretical calculations or predictions of what's going to happen in the future. And I think what you might find the most interesting depends on what you're the most interested in. Right now, I'm really into the theoretical calculation papers and the predictions for future data, so I'm finding those to be much more interesting. But personally, I always have a soft spot for people who pull out old data and are like, look what we found in this data from 10, 20 years ago, because that's always really nice as well. So I think that's a very cool question, Paul, and my answer is a bit of everything. Both options and a secret third option. So cool question. Okay, let's see, more questions. There were more questions here. Yes, Breath, feel free to ask your white hole question whenever you want. So, Matteo, anything interesting happening in cosmology in the last year or so? So, I did a stream a couple weeks ago called Cosmology in 2024, and it was a summary of what had happened in cosmology in 2024. And I think the key results for me in 2024 were the new DAISY results, which are potentially very, very interesting. And there was the first release of Euclid images, which were not the cosmology results, but just some first kind of like side quests that Euclid did, which I thought were very interesting as well. Then, of course, there's a whole debate about the Hubble tension, which has been ongoing, as Madeo is well aware, has been ongoing for many, many years. And in the last year, there was the thing where there's a question of does JWST give the same conclusions as the Hubble Space Telescope in terms of the expansion rate when calculated with supernova? And depending on which team does this analysis, you get different results. So that is pretty interesting. And I think those were the three main things that happened last year. Then there's also a paper that came out recently-ish, a couple months ago, that claims that, which I've also discussed briefly here in the stream, there was a paper a couple months ago that claims that there's a modified gravity model that fits the cosmological data better than Lambda CDM. However, they had a very specific data set of data included. And for an example, the CMB was not included in this analysis. So I think those are the main things. I personally don't think there's been any papers in the last 6 months that I've been like, wow, this is groundbreaking, this is amazing. As always, right, there is slow and steady progress. There's a lot of people making progress in using machine learning to do some cool stuff in some cool calculations that are quite difficult to do. But I personally don't think there's been anything in the last 6 months to a year that I think is groundbreaking or going to break cosmology and change the field forever. But there has been some cool things like DAISY and Euclid. The Hubble tension is always fun to follow. So yeah, that's my conclusion of anything new in the last year or so in cosmology. That's, of course, the summary. I did the full stream of this a couple of weeks ago of cosmology in 2024, where I also talked about some space missions, like some stuff that happened on Mars, which is not really cosmology, but is also very fun. Comment from John here that your cat's head popped up and looked around for who was meowing. Yeah, it was Otto. He likes meowing when he has zoomies. Usually he's the loud one of the two. Good day only screams when he really wants attention, but Otto is very, very loud. Okay, so let's see, going through the questions, just answered the question from Matteo. Let's see, where were we in the comments? There's a question from Mito. Analysis of Bennu asteroid samples showed many amino acids and nucleotides. If they are so common in outer space, it is very interesting, but I fear that they may be contaminants from Earth. Yeah, so I meant to read this paper recently and then didn't. So there's always the ongoing question of, are there the building blocks of life elsewhere in the universe? Because of course we know they exist on Earth. Where else in the universe what might we find them? So there is this asteroid Bennu that we have collected samples from. Not we, like me personally, we have collected samples from and analyzed them, and these samples appear to contain amino acids. Now, amino acids and nucleotides are often considered the building blocks of life, or at least some of the key components needed for there to be life somewhere in the universe. And this adds to the idea that life on Earth might have originated by an asteroid crashing into Earth, bringing these building blocks and like sowing the first seeds or the first building blocks needed for life to eventually form. Now, of course, in any of these analyses, we have to be really, really careful that we're not adding things to the system when we're doing the analysis. I have not read the recent paper on Bennu, so I'm not sure about this, but I would guess that people are being very careful with this. And of course, this is something that needs to be cross-checked and needs to be verified and confirmed by other teams. But there is always a problem of in general, when we send any probe to space, any mission, what are we bringing along with us? And this is something that is especially important as we start exploring other places. One example we can give of this is, there are tardigrades on the moon. So tardigrades are little baby space bears that, well, we call them space bears. They're little tiny microbes that can survive pretty much everything. They can survive extreme heat, extreme cold. They can survive extreme radiation. Sorry, one sec. My cat has figured out that there is one way to always get my attention, which is to open the door to the trash room. He never does this, like he never opens it when I'm out. When I come home, it's always closed. He only does it if he feels like I'm ignoring him. And apparently I'm currently ignoring him, so he's trying to get into the trash. Now he's just staring at me like, come and stop me. So yes, he's being slightly disruptive. So yes, tardigrades are these little tiny microbes that can survive extreme temperatures, extreme pressure, extreme radiation. And there was an experiment that took some of them to the moon to see how they would do in that environment, but that mission crashed. So there are basically now tardigrades loose on the moon, so to speak, which means this is a contaminant that we brought with us. If then we go to the moon and we could be like, hey, look, there's a tardigrade. It's like, yeah, we brought it with us. So of course, when analyzing the samples of Bennu, if people say we found amino acids, we have to be really careful that that's not something that hitched a ride on the probe that recovered these samples, right? That this is something that actually is from Bennu and not something that we accidentally took with us when doing this experiment. But it is very exciting to see that there is potentially, these amino acids are potentially common in the universe, because it makes it more likely that there might be some other life forms out there, ranging from anything from microscopic organisms to, advanced civilizations. Of course, I'm not saying by any means that we have found any evidence of advanced civilizations, just to be clear here. People have found that the samples of the Bennu asteroid may contain amino acids. So let's be clear here. Comment from Scott here, something dark energy and cats have in common, neither behave the way we expect them to. That is very accurate. Yes, sometimes the cats like getting up to mischief. Okay, sticking with amino acids before I go back to the other questions, I'm just going to answer some related questions and then go back. Hey, Lothargo, great to see you as always. Question from John here related to the amino acids. Can we detect those kinds of amino acids spectroscopically from remote sources, or is it only in sampled materials that they can be detected? Usually for these amino acids, you actually need the sample materials, because amino acids are ridiculously small microscopic things that you need to be able to put under a microscope. Now, with spectroscopic analysis, where you look at kind of the chemical composition of atmospheres of different planets and things like that. With this, you can get the idea of, are there the overall ingredients? For example, is there oxygen? Is there nitrogen? Is there hydrogen? Is there carbon? These are kind of the four elements that we think are necessary for these amino acids to exist. Of course, we have also found amino acids that don't rely on this. So we can do spectroscopy to say that, okay, this asteroid, for an example, might have carbon, but then to actually see if it has amino acids, we need to be able to do the analysis. We need to be able to put them under a microscope. There's a lot of cat hair in my house today, despite the fact that I clean today, which means I constantly have cat hair on my throat, and that's why I'm coughing. Yeah, so we can do spectroscopic analysis to figure out the overall composition of planets, of asteroids, or of moons, of things like that. But in order to look for amino acids themselves, we actually need to be able to put something under a microscope, because an amino acid is a microscopic organism. Give me 1 sec, sorry. Okay, that's better. Just had to clear my throat, and I always mute myself, or try to, so that I'm not coughing into the microphone. Comment from Scott, my oldest cat knows that starting to rip up paper is how to get my attention. Yeah, the paper that they were after is inside the trash room. So I think the first step is open the trash room. The second one is find what he can rip up to gather my attention. Now he's calmed down a bit. For now, we'll see. The other one's just chilling. They take turns. They either both have zoomies or one of them has zoomies, but it's rare for them both to be chilling. Comment from Paul here. You said earlier DESI data implies evolving dark energy. Is it pointing towards increasing or decreasing dark energy over time? Would this be the difference between Big Rip versus cyclical universe? Great question. So I'm trying to think. I think the idea was that dark energy is slowing down. Yes, dark energy is slowing down, so the expansion is no longer accelerating as fast as it was in the past, according to the DESI results, which are not a 5 sigma, so not enough to indicate a discovery yet. It's kind of at like 3 to 4 sigma, depending on the data sets you use. The sigma is the degree of belief that we have in something, and we usually only say it's a clear discovery above 5 sigma. The DESI results are not there yet. So the DESI results indicate that dark energy is slowing down. It is gradually getting slower. It is thawing, was the phrasing that they used. As to what this says about the eventual fate of the universe, that is still a bit unclear. So there are several different ways the universe could end. 1 sec. Now, the other cat has found a slightly open trash room. As I said, one is calm, the other is not. And they take turns. So, yeah, at some point, unless I go close that trash room, they're going to pull out some of the trash. Cats make everything much more fun and much more disruptive. But that's okay. They're very good cats. They just like being disruptive. Yes, so there are several different ways the universe could end, and it mainly depends on what dark energy is up to. So one possible idea that people had considered for many years is what is known as a cyclical universe. So we know that the universe is currently expanding, and this expansion is accelerating. So if we just focus on the expansion of the universe for now, there was the idea for many years that this expansion at some point would slow down, it would gradually stop, because it's a battle between stuff being pushed outwards and gravity pulling things inwards. So the idea of the cyclical universe is that at some point the expansion would stop, it would slow down enough that it would stop, and then the universe would gradually collapse back upon itself into what is known as a big crunch. This big crunch would form a big bang that would start the new universe. So then you have a universe that is constantly expanding and shrinking, expanding and shrinking. However, we know that the universe is not only expanding, it is currently going through accelerated expansion. So it is expanding faster today than it was in the past. This accelerated expansion means that the cyclical universe is quite difficult to realize, because not only would you would basically need to turn dark energy off completely and then allow the universe to recollapse. So given that we know that the universe is undergoing accelerated expansion, which we think is caused by dark energy, it makes a cyclical universe less likely. So once we've discarded the cyclical universe and we accept that the universe is currently undergoing accelerated expansion, that leaves 2 main ways the universe could end: what is known as the Big Rip and what is known as the heat death. In the heat death, the idea of the heat death is the universe continues expanding at its current rate forever. This means that things gradually get further and further apart to the point where there will be no exchange of energy, no exchange of heat, no exchange of information. The universe would end up a cold, empty, desolate wasteland. Basically, everything would be pushed so far apart that it could no longer interact with everything else. So you'd still have stars that would eventually burn out. You'd still have galaxies that would eventually fade out as all the stars burnt out. So you would end up with everything so far apart in the sky that it just can't exchange information. And the universe would end up dying, being a cold, dead wasteland. It's either called the Big Freeze or the heat death, the death of heat, depending on your perspective. Another possible way the universe could end is the Big Rip. In the case of the Big Rip, the accelerated expansion of the universe increases so much that it becomes possible to break apart the atomic bonds that holds everything together. This means that galaxies would be thrown apart, and eventually planets would be pulled apart, stars would be pulled apart, even black holes would be pulled apart. Everything would be torn apart at its seams. The universe would basically be ripped apart, and there would be a cold, dead, empty universe that doesn't have anything in it. There's no structure left whatsoever, just atoms drifting throughout the universe. So this is another possible way the universe could end. So the new DAISY results do not say that it's much more likely to have a cyclical universe, but between the heat death and the Big Rip, the difference between these is basically what is dark energy going to do in the future. If dark energy continues doing what it is now, then we end up with the heat death. If dark energy increases, then we could end up with a Big Rip scenario where the universe is ripped apart. The DAISY data indicates that dark energy is slightly slowing down. It would not be enough to lead us to a cyclical universe, but it could be enough to guarantee that we end up in the big freeze, the heat death, rather than in the Big Rip. But again, the DAISY results are not confirmed yet. Well, they're not yet at Phi Sigma, and it is DAISY year 1. So 1 year of DAISY data. They are already working on the year 3 data release, which is expected to be this year already, because they've already finished collecting 3 years of data. Processing the first year of data took longer because they still had to develop all the techniques and everything. Now that they have all of that, analyzing the first 3 years of data is going to be much faster. So we do expect there to be an update from DAISY potentially this year, maybe early 26. Okay. Keeping on with the questions, I know there were a couple of others I wanted to get to, so I'll come back to those in a minute. My cats have disappeared and have gone suspiciously quiet. Comment from John here. Would Euclid be expected to be able to detect evolving dark energy like a confirmation to DAISY? So Euclid is looking at slightly different aspects of dark energy and of cosmic evolution. There is going to be a bit of overlap. Euclid has mainly 3 different ways of measuring things, and one of those will overlap with the DAISY results. So it's not necessarily the case that Euclid can confirm or deny DAISY, but it can add another data point with similar data that could help shed light on this question. But I think timeline-wise, we're much more likely to get DAISY year 3 data before we get the first cosmology results from Euclid. They might be on the same timescales, but I think DAISY year 3 data will be out before Euclid year 1 data. But in any case, it will be another data point. It's not necessarily, they're not doing the same thing. So even if Euclid then doesn't find time-evolving dark energy, it still doesn't explain why DAISY did. So it's not like one of them can refute the other. If they both find hints of time-evolving dark energy, then that makes the case a lot stronger. So, but if Euclid doesn't find it, it doesn't rule out the DAISY results. So there is going to be some overlap with the results, but not substantial enough to say that one can supersede the other. Okay, I'm going to go back up to some questions and then get to the white hole question here. So where was I? Let's see. There should be a way in Restream to mark like which comment I last addressed, and then it would be easier to move around. Okay, there was a question from John about AGN. So do AGN accretion disks produce metals in a significant way? I was wondering if primordial or direct collapsed black holes could have been enriching the dark age IGN with metals. This is a very cool question. So AGN are active galactic nuclei. We believe that a lot of galaxies, like the most dense and highly energetic galaxies have what is called an AGN, an active galactic nuclei. This is basically where you have a supermassive black hole at the center of the galaxy, and the whole thing is spinning quite quickly. So this leads to an accretion disk around the AGN, which is a lot of superheated matter spiraling around this black hole and gradually falling in. As this matter spirals around the black hole, it can get accelerated. This acceleration produces synchrotron radiation or other types of radiation, which produces two jets coming out from the AGN. So if you imagine, I'm going to use my black hole here, but let's just pretend it's got stuck. Let's just pretend that this is an AGN here. So we have our active galactic nuclei, we have the accretion disk. As particles or matter is going to swarm around here, it's going to accelerate, and then shoot out in this direction and in this direction. So you end up with two jets going out of the AGN. If these jets are pointed directly towards Earth, they could be very damaging, depending on the direction on which these AGN are pointing, or depending on the angle on which we're observing them. We classify these as either blazars or quasars or different types of active galactic nuclei. So where were we? Question about AGN. Can they produce metals? I don't think you can produce metals this way because you are not fusing elements together. So while you are accelerating particles, these are gaining energy, then there's magnetic fields involved, these get shot out. In order to produce metals, this is what we do at the center of stars. And the way that this is produced is by fusing together elements. So you have enough energy, you have enough heat, you have enough pressure that you can fuse elements together. This is a huge amount of energy involved. You are in order to push hydrogen together to form helium. This is something that we have not been able to reproduce in a stable way here on Earth. We're not yet at the stage of having a fusion reactor, but it is stuff that happens inside stars. So I don't think there would be enough energy to produce metals around the accretion disk, but the AGNs themselves are also not going to produce metals because they're not stars. Well, I was just thinking out loud there. The AGNs themselves are supermassive black holes at the core that are then pulling everything else around it. So the black holes themselves are not going to be forming metals. And even though you are accelerating the particles to really high energies, you don't have the sufficient pressure in an accretion disk to be able to create metal. So I don't think that you can produce metals in the accretion disk of an active galactic nuclei, but that is a very cool question to think about. And then the second part of the question, you were wondering if primordial or direct collapse black holes could have been enriching the dark matter IGN with metals. So what you can have is these initial stars that when a star reaches the end of its lifetime, it can collapse or explode as a supernova, and this supernova explosion can carry metals throughout the galaxy, throughout the universe, because these are the ones that were formed inside the star and then added to the overall surrounding area. So if you have an active galactic nuclei, you could have a lot of stars in the accretion disk, and these stars in the accretion disks could be producing metal. But then you kind of need a chain of events. You need a star to kind of die in or explode as a supernova while caught in the accretion disk of an AGN in order to enrich the accretion disk with metals. Cool question. So I think short answer is no, we don't expect AGNs themselves to produce metals, but there could be some knock-on effect whereby they capture a star that is producing metals. So my answer is no, but maybe yes, but probably no, if that makes sense. Okay, going to the new questions, and I'll go back to the other ones. Following up with this one, comment from Scott here. How close together are stars near galactic cores? Close enough to not allow planetary systems. So the universe is very, 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 very big and very, very, very empty. We look up the night sky, we see millions or thousands of stars. The closest star to us is 4 light years away. It would take us 4 years traveling at the speed of light to reach the nearest star to us. Stars are very, very far apart. As you get to the center of a galaxy, it's going to be more populated, but it's still going to be really, really far apart. This is something that most sci-fi shows get wrong about space. Space is empty. If you're flying through an asteroid field, you'd see an asteroid every day if you're lucky. It's not like you have to dodge them. I know it makes for a more cinematic TV if you're kind of in a space race around the asteroid belt. The space is empty. There's a lot of empty space in space. So if you're in an asteroid field, you're not going to be bumping into asteroids every other second. Even if you're close to the center of a galaxy, you're not going to be bumping into stars every second. Zoomies have continued. So yes, the stars at the center of the galaxy are more compact, they're closer together, and this will impact planetary systems slightly, but not dramatically. Because in order to really impact the ability of a star to have a planetary system, you'd need the stars to be close enough to kind of orbit around each other. And once you get so close to the center of the galaxy, the main gravitational force is going to be coming from the supermassive black hole at the center of the galaxy. So I think the biggest disruptor to the planetary systems is actually going to be the supermassive black hole and not other stars being too close together. So even though stars are more dense, or like there's more stars at the center of galaxies, there's not going to be enough of them for it to be a big problem for planetary formation or like planetary systems, but you will have other problems to deal with, like the fact that you're very close to a supermassive black hole. So yes, that's a very cool question there, Scott. Going back to the AGN question from John. So maybe if an AGN rips a star apart in a tidal disruption, then the jet could distribute its metals much further than a supernova. Yes. There's a few things need to happen here, but yes. If you have a star that is at the metal forming stage that gets sucked into an AGN accretion disk and then gets ripped apart by the AGN tidal forces, then the metals could contribute to the AGN disk, to the AGN jets. Yes. It's several things that need to happen in order for this to be the case, but it is possible. Yes. There was a question from Mateo here about Dizzy. I know there's a couple of other questions I need to get to, and the white hole one from Perth. Question from Mateo: are the Dizzy results compatible with other data sets like the Dark Energy Survey, or are there tensions? Very good question. Overall, they are pretty compatible, mainly because they are the first ones to have this level of precision to look at this type of equation of state of dark energy. So the main thing they are looking at is the equation of state of dark energy. So how dark energy behaves does it behave like a perfect fluid? Does it behave differently? This is measured with what is known as the equation of state. Now, there have not been any hints before of time-varying dark energy, but DISY has the biggest survey of this kind. So the Dark Energy the Dark Energy Survey DIS a few years ago was looking mainly at weak lensing, whereas DISY is using BAO. So these are terms that I'm just going to clarify slightly, but just for Mateo, because they're using different measurements, they are not necessarily in contradiction or in tension. So to clarify this a bit more, DISY, the Dark Energy Survey, was a space-based mission that looked at a lot of galaxies, and it mapped how these galaxies are distorted due to gravitational lensing. So when you have a big, massive object that in space, this can distort the path that light takes. Light doesn't feel gravity per se, but it feels the curvature of space-time. So yeah, light feels gravity in that sense. So if you have a big, massive object, for example, a clump of dark matter, even if light doesn't feel the dark matter can curve space-time, so light experiences the gravity caused by the curvature of space-time, so the light is distorted, and this leads to distorted images of the galaxies. So DES, the Dark Energy Survey, was looking at this distortion of galaxies. With this, it was taking measurements of the evolution of structures via the weak lensing experiments. Now, I do believe that they found no hints of time-varying dark energy with this, but it's done with a completely different technique. Now, the DISY results use BAO. So BAO is the average distance between galaxies. This is a scale that is implanted in the night sky. And we look at how far apart galaxies are. We look if there's a number that appears more frequently than other numbers. And if so, we identify this as the BAO scale. And then we can use that to get ideas on how the universe is evolving. So they're slightly different techniques. Sorry, one sec. So they are slightly different techniques, but DS, the Dark Energy Survey, was very compatible with Lambda CDM and Planck. DISY is not compatible with lambda. Well, it is still compatible with lambda CDM, but it finds a preference for non-lambda CDM, where lambda CDM is our standard model of cosmology. DISY is pulling us away from lambda CDM, whereas this didn't. So you could argue that they are producing slightly different results, but because they are looking at different probes, their data is not necessarily incompatible, and it can be combined. And I think they do actually combine it in one of the papers potentially, and it reduces the preference slightly for time varying dark energy. I think I can't remember completely. So I would say that the DISY results are not in direct tension with, for an example, DIS, but they are, of course, in tension with Planck, which from the CMB mission, which gave us this map here, because this figure here, this data here, does prefer lambda CDM. So while, again, they're measuring very, very different things, you can argue that if the CMB is giving us lambda CDM and DISY is giving us non-lambda CDM, there is a bit of tension here. But of course, with CMB data, we weren't directly measuring the equation of state of dark energy. So I would say that DISY is not really in tension with other data sets. It's a new piece of the puzzle that gives us new data that will hopefully be confirmed when we get the year 3 data. So I would say DISY is not in tension directly, but it does not necessarily match with previous results. I guess then it really depends on how you define tension. Like, I would say the tension between different ways of measuring the expansion rate of the universe is there because you're measuring the same base quantity, which is the expansion rate of the universe, but again, the way you measure it is different. But you expect the final number that you get out to be the same. Whereas in this case, because the overall thing, the observable, is different, I would argue that they're not directly in tension, but I think you could argue that potentially they are in tension. Hey, Gwyneth, great to see you here as well, another regular coming in. Okay, back to the questions. Where was I? Let's see, I keep jumping around with the questions, but... Okay, comment from James. Basic problem, I can't seem to grasp how the universe expansion is faster than the speed of light. Is this only because the expansion started before light became free? This is an excellent question here, James. So we know that the universe is currently expanding. This expansion is accelerating. Now, currently, the universe is not believed to be expanding faster than light. But this is something that is quite difficult to talk about because thanks for stopping by, Scott, and have fun. Have a good evening. So when we say that nothing in the universe can travel faster than light in a vacuum, this applies to things traveling in space-time. It does not apply to space-time itself. So there is no constraint on how fast space-time can accelerate or how fast space-time can expand. Also, when we talk about the expansion of the universe, we always talk about the rate of expansion, like how much it's growing per volume, per second. So we give it in units of what is like megaparsec over kilometer per second, which basically is like length over second. So it's 1/second. So it's an expansion rate, not an expansion speed. And we don't normally talk about how fast the universe is expanding in terms of speed or velocity, because then we need to ask the question of with respect to whom. Because we know that every velocity, every speed in the universe is relative. If you're on a train traveling and you throw a ball, you're going to measure that ball's velocity differently to someone on the platform because you subtract the motion of the train because you're on the train, where somebody else adds the motion of the train if they're off the train. We know that velocity and motion is relative. So if you want to talk about how fast what's the speed of the expansion of the universe, the question is with respect to whom. You cannot put yourself in a frame outside of the universe and call that an absolute frame, because you cannot be outside of the universe when the universe by definition is everything in existence. If you put yourself in the frame where you're traveling with the expansion of the universe, then would you even measure the expansion of the universe? So it is very hard to talk about a speed of expansion for the universe because we can't really attribute speed to something that is all of space-time. When we're talking about speed, we're talking about distance over time. We're talking, how does that relate to space-time? And we already have space and time there. If space-time itself is expanding, how do we give a velocity to that? So My first answer to that question is the universe is not expanding faster than the speed of light because we cannot attribute a speed to the expansion rate of the universe. But my second answer would be even if you could, and you found that the universe is expanding faster than the speed of light, which, if you calculate the volume or how quickly we think the universe expanded during inflation, is a claim people can make, then there's no reason why it couldn't, because the limit of nothing in the universe can expand faster than light in a vacuum applies to things traveling through space-time, but not to space-time itself. So, short version, the universe is not expanding faster than the speed of light in a vacuum because we can't talk about how fast the universe is expanding. We always talk about the rate of expansion. Although you will often hear me say the universe is expanding faster today than it is in the past, because that's easier to say than the rate of expansion has increased. But we cannot really attribute a speed to the expansion of the universe, and even if we could, there is no upper limit because the only limit is on stuff traveling through space-time, not on space-time itself. But that is a very, very cool question. It is a very cool question to ask there. So let's see, where were we? That was a question from James. Where are we? The comments. I keep jumping around the comments today, and I'm finding it very hard to figure out where I am in the comments. Where was I? Okay, we talked about this, yes. So it's a very good question, James. My short answer is don't worry about it. The universe is not expanding faster than the speed of light because the universe doesn't actually have a speed of expansion. It has a rate of expansion. Well, my cat's gone. Weird. Okay, let's see. There was a question from Ben. Why is the discovery of quantum gravity so important? Who would benefit from its discovery, and how close are we to discovering it? That is an excellent question there. So, how close are we? I would say we're not close yet. Now, the reason it's important is because we don't know how gravity works, really. Realistically, we don't know how gravity works. Thanks for dropping by, my dear. It was great to see you here. Yeah, hope to see you soon. Absolutely. You know where to find me. Come to Finland. So, yes. So we don't know how gravity works. We have some ideas, but we really don't know. So let's just take it back a step here. The universe has four forces that we know of. There's some forces we're more used to than others. For an example, I drop pen falls down. We stay in orbit around the sun. This is gravity. Another force in the universe is electromagnetic. We have light. We can put a magnet on a fridge. Electromagnetism, understood. Then we have the two nuclear forces, the strong nuclear force and the weak nuclear force. The strong nuclear force is responsible for holding everything together. It glues quarks together inside protons and inside neutrons. It glues neutrons and protons together inside atoms. It's a strong force. It glues things together. Then we have the weak force. The weak force is responsible for radioactive decay and for neutrinos doing whatever they want to do. Four forces that govern the universe. Three of these have an associated particle. We know how they behave on the quantum level. And these are the weak force, the strong force, and the electromagnetic force. Anytime there's electricity or magnetism involved, what is happening is a photon, a particle, this particle of light or this electromagnetic particle is being exchanged. So when you see something, it's because there's a photon coming to your eyes. In terms of the weak force, we have three bosons. We have the W plus, W minus, and the Z boson. These are the ones that carry the weak nuclear force. The strong nuclear force is carried by a particle called the gluon. The gluon glues things together. All of these particles are bosons, which means they tell the other particles how to behave. They're the ones that give the rules to the other particles. We also have the Higgs boson, which gives everything mass, but that's not associated to a force. But then how does gravity fit into this picture? We don't know how gravity behaves on the quantum level. We don't know if there's a particle involved in gravity. When there's a gravitational wave, a ripple in space-time, is this a field of particles in the same way that you have a light field or a light beam that is a string of photons? We don't know the answer to this. And the reason for this is because the scales are very, very different. When we're talking about gravity, we're talking about massive things. We feel the gravitational force of the sun, which is many, many, many kilometers away. But with other forces, we think on much smaller scales. The strong nuclear force is holding things together at the atomic level. The weak nuclear force is something that happens again at the atomic level. Even the electromagnetic force, like, sure, we can see electricity, we can see photons coming from the other side of the galaxy, but we know that this is because there's a photon traveling throughout there. So the question is, what is gravity up to? How does gravity work on a quantum level? From Einstein's general relativity, we say gravity is the curvature of space-time. Does that mean that gravity is just a geometrical concept? Does it even have a carrying particle? We don't know. So quantum gravity would be a theory that could explain how gravity works on the quantum level. It would answer these questions of, is there a particle? Are there just strings? Are there, different things happening here? We don't yet have an answer to these questions, so we don't yet have quantum gravity. Who would it benefit? Well, it would benefit anyone interested in figuring these things out, but also it would allow us to do cool things. Like, if we could understand which particle or how gravity works on the quantum level, we would be able to more easily manipulate gravity. We would then be able to do things like maybe make an anti-gravity field. It could potentially also help with space travel. So the main applications of quantum gravity, for one, is understanding how gravity works, because it's the force we're most used to. So it would kind of be nice to understand how it works and how it relates to the other forces. And then it could potentially help us master gravity and come up with ideas on how to make an anti-gravity field or how to do things like that, similar experiments. As to how close we are, I think we're quite far away. The problem is there's a lot of different models and theories, or like models and ideas for quantum gravity, but a lot of them require either extra dimensions or things that we don't have in our universe. So they become things that mathematically are very cool, but physically are quite hard to realize. So not sure if you're going to see a cat's about to jump up here. So I think quantum gravity is something, there's a lot of people working on it. I would like to see advances in quantum gravity in the next 50 years. Realistically, I'm not sure if we're going to. So it's a very, very cool topic, but I'm not sure how close we are to having any type of resolution to quantum gravity. Potentially, as we get more and more experiments looking for gravitational waves, maybe we'll have more things there. But it's I think realistically, we're not there yet, but potentially sometime in the future. Following on with this, there's a question from David Howden. I know I've asked before, but I've obviously not grasped the explanation, but why is the distance of the strong force limited? This is a very difficult question to answer. It's a very good question, David. I think you might have asked it before, and I might have given the hand wavy thing of this is difficult to answer. And I'm also not going to give a convincing explanation to it today. The answer is basically due to quantum things, but that's obviously not very satisfying. But we know that the strong force is very, very strong, and it is contained. There is this kind of confinement. While the electromagnetic force travels, you have these photons that can travel. The gluons do not separate too much from the quarks. Usually what you find is what is known as a quark-gluon plasma, where the quarks and the gluons kind of form this soup. So inside a proton, you have the quarks, the ups and the downs, but you also have a sea of protons. Sorry, of gluons, a sea of gluons. And these gluons are the ones that are giving it this kind of structure. So it's not necessarily that you just have the quarks and a gluon. You have a soup of gluons that is confining it to that space, which doesn't really help answer the question. But a good way to think about it is photons are particles that are traveling at the speed of light doing whatever they want, while gluons are kind of like a soup a hazy dust that sticks around a thing. And that's also why it's very hard to separate quarks, because if you try to pull two quarks apart, the gluons are going to fight to keep them together, and the amount of energy you need to put in the system to pull these quarks apart is enough to actually create more quarks, which is why you can't just say, like, here's an up, here's a down. You usually find them together. You always find them together, not necessarily an up and a down, but you find a mix of them, because the energy needed to separate them is too much, because there's this kind of gluon treacle or gluon syrup holding them together. So I know this doesn't really answer your question, David, as to why the strong force has a limited distance. It does, quantum reasons. I'm not going to be able to give a convincing explanation, because I always have to stare at the equations for it to make sense to me again. But you can think of the gluons as being kind of this soup, this this dense thing that holds stuff in place, whereas photons and the other bosons are usually traveling more freely. So it doesn't really answer your question, but quantum things happen and gluons get confined. Yes, that's my answer. Gluon quark confinement, which is not a real answer, but yeah, that's the best I'm going to be able to do today, I'm afraid. Now, that's a very cool thing to think about, David. And don't worry if you don't understand that, because as you can see, I'm struggling to explain it. It's one of those things that in physics was just like, that's cool. It's one of those things that you understand, but also it's like we do understand it, but that knowledge is always like just on the outskirts of my brain and not completely reachable. It's like how magnets work. I know how magnets work. I've taken whole courses on how magnets work. But if someone asks me how magnets work, I'm always like, it does. It's I know this is practically a meme at some point. How do magnets work? Yeah, it's one of those things that is somewhere in my brain, but not in a way that I can give a good explanation. Okay, back to the questions. Where were we? Let's see, we covered AGNs, we covered the expansion of the universe briefly. We covered the cats being very active. We were talking about quantum gravity question from Ben. That's where we were. Okay, there was a question from John. I'm about 40 minutes behind with the question, but I've been jumping around through the questions. There's a question from John at some point. Is there expected to be red dwarf population 3 stars, or would all of them have been short-lived giants? I am not sure. So a red dwarf is a type of star. That's a very, very, very sciencey answer. Red dwarf is a type of star. I forget things about my astrophysics in terms of stellar evolution because it's something that I'm not a specialist in. I'm not an expert in stellar evolution, so I can't give a convincing answer to that question. I'm currently trying to remember the different why there are population 1 and population 2 red dwarfs, so I can't even answer why there are question 3 ones. Why there are population 3 ones, sorry. So yeah, that's a good question. And my answer is I don't work on stars, so I don't know, but that's a cool question. At some point years ago, there was an expert on stellar evolution on the stream. We should try to get someone back to do those type of questions. It's a cool question, John, but I don't have an answer to it, I'm afraid. Okay, going back through the questions, where were we? I'm doing quick fire questions now. I think I've answered a lot of them. Okay, and then there's a question from Press. Now, before I get to the question from Press, let me just check what's happening down at the bottom, and then I'm going to go and read the white hole question, which I'm sure is going to be a difficult question to answer, because Press, you always ask me difficult questions to answer. Okay, coming from David Howden, quantum things happen. Yeah, that is a good answer. You know, sometimes, no, I'm going to be very careful with what I'm going to say here. Please don't blame quantum effects for everything happening in your life. This is not like Mercury is in retrograde, there's quantum effects happening. But usually, if there's a particle physics question, the answer is going to be quantum effects. So if you're asking, why does a particle, why does light, why does a force, you can answer this with quantum things happen. But please don't use that as like a catch-all phrase of like, you know, the quantum effects are wrong. It doesn't apply to your life choices, but if there's something about physics you don't understand, there's a high chance it's because of quantum shit or quantum stuff happening. So yeah, quantum stuff happening. As Paul is saying here in the comments, I don't work on little things like stars and galaxies. I work on big things like the whole universe or the tiniest things inside the universe like particles. I'm on the extremes. I don't do the part in the middle. But yes, I don't work on small things like stars and galaxies. They're too small, but also they're too big because the gravitational waves I'm looking for are smaller than those things. But yes. Yeah, I feel like you know when you say like the vibes are off, the vibes are wrong. The particle physics version is the quantum stuff is happening, which amuses me slightly because you do have vibrations in quantum physics, so the vibes are literally wrong. Anyway, tangent, random tangent. Quantum things happen or they don't. Exactly. Quantum things may or may not happen. Coming from Perth here, and then I'll jump to the white hole question. Coming from Perth. Quarks resulting from virtual particle generation could be isolated, right? It would be statistically unlikely for the accompanying gluons to also be generated right next to it. Good question, Prath. Quarks resulting from virtual particle generation could be isolated. Yes, technically. Could they? Could they, though? And now I need to think about that because you shouldn't have, like, technically, you can't just have quarks. You always need to have a quark and an anti-quark, or you need some type of symmetry. You can't find unbound quarks. But can you produce unbound quarks in virtual production? I would say no. I would say that even in virtual particle generation, where you kind of borrow energy from the universe to produce a particle, and then these particles immediately annihilate and pay back the universe the energy that was borrowed from the universe. Could you have deconfined quarks? I'm gonna ask an expert, which is not me. I am an expert, but not an expert. It's like when you look for an adult to your adults. I will ask this question to someone who knows more about quarks than I do. That is a cool question, but I'm making a note of this of quark confinement confinement in virtual particles, because that is a good question, and that is a question that I'm absolutely not going to be able to give a good answer to. But cool question. Speaking of cool questions, let's go find the white hole question. Okay, comment from Prath. Remember a few months ago when we spitballed white hole pair dynamics and thought two white holes can't orbit each other? Yes, I remember thinking about that for quite a while. What if they can? Because negative mass attracts negative mass. Okay, so let's go back to some ideas of black holes and white holes here. So black hole, region of space-time that is so dense that nothing can escape, not even light. You'd have to move faster than light in a vacuum in order to escape the gravitational pull of a black hole once you've crossed the event horizon. Nothing in the universe, to our knowledge, can travel faster than light in a vacuum. Therefore, nothing can escape the gravitational pull of a black hole once it's crossed the event horizon. Once you're close to the event horizon, you can still get away, but once you cross the event horizon, there is no escape. Now, a white hole is a hypothetical opposite of a black hole. This is exactly why I have this black hole, white hole plushie here. So it's a theoretical opposite, and instead of pulling everything in, it would push everything away. So a black hole pulls everything in. A white hole would be the mirror opposite, so it would push everything away. White holes would also potentially have negative mass. Now, white holes are one of those things that are a valid solution to Einstein's equations of gravity. So you can use Einstein's equations of gravity to pull out black holes. This is something that exists within the mathematics of general relativity. White holes are something that exists within the mathematics of general relativity, but it's something that is a lot harder for us to talk about in terms of do they exist inside our universe, because we know that black holes exist. We've been able to measure a lot of things about black holes. I feel like these faces should be opposite, so that if I turn them like that, the faces would be right. Instead, I have to turn it on that axis, which does make a lot more sense, but it's just not as fun. Tangent. So black holes are something that we have observed in the universe. White holes are something we have not yet observed in the universe. But it's something that mathematically makes sense, but that doesn't necessarily mean theoretically it does make sense. And there is some idea that anything that falls into a black hole in our universe is kind of spat out of a white hole in another universe, which is also something that is difficult to conceptualize. And we often draw a Penrose diagram where we kind of have space here and time going upwards. So if we think of, we could be here, we are here, this could be the black hole. So anything inside here is inside the black hole. These lines denote the event horizon of the black hole, and outside here, you're outside of the black hole. Then if you reverse time, you could end up with a white hole. Now, of course, you can't reverse time, which is why we often say that this white hole here could be like the theoretical opposite of a black hole, but not something that we might necessarily expect. Okay, so that was just to remind people what are white holes. So what was the question again? I've already forgotten the question. Right, if they have negative. So when we were talking about them before, there was the question of We know that black holes can spiral around each other. Can white holes orbit around each other? And the answer is likely the answer that we came up with was probably not, because to spiral around each other, you need a gravitational attraction, whereas white holes do not have a gravitational attraction. So, new question from Prath: what if they both have negative mass, and the negative mass attracts each other? So then, my question is, how would this work? Because if if you have negative mass, what would make these negative mass objects attract each other? So we know that positive mass and positive mass attracts because this is how gravity works. What would negative mass look like in terms of the equations? How would you put negative mass into the equations? Would you still have an attractive force? I don't know the answer to this question. It's a very cool question, but I'm not sure. So, can we even have negative mass? Is this something that makes sense in our universe? We know that there are antiparticles, but could there be anti-mass? What would anti-mass actually be? Okay, following on with this from Pratt, can negative mass planets or stars be derived from Einstein's equations, or can negative mass only result in white holes? So I don't think you can have any stars or planets or anything like that with negative mass, in the same way that a white hole itself is something that is a hypothetical concept, because we don't know how to visualize negative mass in our universe. And I'm just gonna check something here. Just want to check white hole and mass. And I start typing white hole into my search history, and I find that I've asked a lot of questions about white holes before, probably prompted by these conversations. Yeah, so do white holes actually have negative mass? Is the question I'm currently thinking about. Yeah, yeah. So I think the problem here is really, how do we visualize negative mass? What does negative mass mean? Now, when I asked people in the office about this, I was told draw a Penrose diagram and look at what's happening in the Penrose diagram, and that didn't help. But yeah, so the original question was, do orbiting white holes produce gravitational waves? And based on some papers that I found, yes, orbiting white holes should be able to produce gravitational waves, potentially, but they probably wouldn't manifest in our universe, we think. So, white holes are weird. We kind of think of white holes of having negative energy, which means they would have negative mass. But visualizing something with negative mass is quite weird. What would an object look like where everything is pushed away from it? As John is saying here, if white holes existed, wouldn't they be very bright and visible? Well, they wouldn't necessarily be bright, because they would just deflect. Anything going near them would be deflected. If you imagine this is a black hole, right, and you're traveling like this, you're going to be attracted to it due to the gravitational force. But if you have a white hole and you're traveling like this, you're going to kind of do a slingshot maneuver away from it. So, in that sense, it's not necessarily like emitting light in the same way that a star is. So, it wouldn't necessarily be a bright source. It would just be something that anything that comes close by is immediately pushed away from it, in the same way that a black hole immediately sucks everything into it. Well, not immediately, you need to be close enough. So, white hole is a time reversed black hole that has negative mass, so to speak, but it's very hard to visualize. Uh, Follow up questions here. Is this the same kind of negative mass that is needed to make an Alcubierre warp drive work? I believe so, yes, but I cannot remember how warp drives work, or how they would hypothetically work. Comment from Paul: it seems that if a white hole is a time reversed black hole, it would just have positive mass, just like the black hole does. And then the comment from Pathy: I think mass moving backwards in time would work as negative mass. Yes. So if we're considering a white hole to be a time reversed black hole, that doesn't just mean you wind back the black hole, it means it's a black hole where time travels backwards. And if we're talking about time traveling backwards, then the mass acts as a negative mass. This is also the case with the hypothetical particle known as the tachyon. The tachyon is something that, again, mathematically we can talk about, but physically doesn't necessarily make sense. A tachyon, sorry, is a particle that has negative mass and travels backwards in time. So then, of course, you can ask the question of, are white holes made up of tachyons? But then you'd need a theory of quantum gravity to answer that. So potentially, hypothetically, you could think about white holes being like a massive tachyon, but that also doesn't help to explain all of this. Question from James: are white holes as powerful as black holes? So if white holes existed, again, we do not think white holes exist in our universe. They are very much a theoretical or mathematical construct, but they don't necessarily exist in our universe. But if they did, they would be the same as a black hole, just time reversed. So they would push everything outwards with the same gravitational force that black holes pull things inwards with. So they would have the same effect. They would also have the same effect that they are a gravitational object, so you only notice the effect if you are close by. We have a supermassive black hole at the center of our galaxy, and we don't fall into this because it is quite far away. So even if white holes existed, they wouldn't be pushing absolutely everything in the universe away, only things that are close enough to feel the gravitational force. Coming from what a black hole pulls in time and space, so do white holes deflect time and space? Potentially, yes. Again, so I'm just going to draw this is not going to be a good drawing here. I'm just going to draw the general idea that we have here about what a black hole might look like. Just drawing a sketch here. So if we think of the sheet of space-time here, and we put a black hole in the middle, it's going to curve space-time, and it can create this kind of tunnel because at the center of a black hole, our description of space-time breaks down. So if we think of a black hole as like warping space-time to the point that at the center of a black hole or beyond the event horizon, we can't describe space-time anymore. This is the singularity. This is the event horizon. This is kind of the image that we have of a black hole. So there is the idea that this could then potentially be connected. Now I need to draw exactly the same image here. I'm going to make one black and make one white here. So there is this idea that if you have this black hole here, it could be the symmetrical opposite of a white hole. So the black hole is pulling things inwards from up here, from this perspective here, what is happening to the white hole. So anything that falls in here will come out the other side. This is the basic idea of a wormhole here that connects a black hole and a white hole. But all of this is stuff that mathematically makes sense, but physically is a bit difficult to do. So comments here: white holes cause the universe to expand. Maybe the Big Bang was a white hole. White holes cause universe expansion, dark energy. Yeah, the problem with white holes is it becomes very difficult to talk about because, again, what does a negative mass mean? What does a time reverse black hole mean? It's something I can draw this diagram and tell you time goes upwards, and therefore if a black hole is here, this is the future of the black hole, this is the past of the black hole, this past of a black hole is a white hole. What does this mean? So let's just recap here. White holes are a hypothetical object. They're something that mathematically makes sense. They're a solution to Einstein's equations of gravity, but they are not something that we really know how to talk about in our universe because we just start throwing around terms like negative mass, time reverse black hole, mass traveling backwards, and none of this is something that really fundamentally makes any sense. So white holes are very, very cool ideas, but it's not something that necessarily we can do much with in our universe. So then questions like, do white holes have gravitational waves? According to some papers, yes. What does that even mean? What would these look like? So could you have two white holes orbiting around each other? I'm not sure. Potentially, maybe, maybe not. Let's go back to some more comments here. There was a question from John. I think I covered the other ones. If white holes aren't bright, are there theoretical ways they could be detected? Would they maybe affect the gravitational wave background? Yeah, so hypothetically, if a white hole exists, you would notice it by the way it disrupts objects moving around it. The first evidence we had for black holes was the way that objects the path of objects was affected when they got closer to the center of galaxies. So you could see something similar where you'd have this kind of deflection of any particle. Instead of being deflected towards the object, they'd be deflected away from the object. So hypothetically, there are gravitational signatures of white holes that we could look for, but again, these are ones that we haven't yet found, and we don't really expect to find them within our universe. I like the comment here of maybe supersymmetric particles have negative mass. Let's not go there. Also, understanding quantum gravity would help us understand more about these things as well. So white hole and black hole orbiting would be cool because their waves would cancel each other out. Would they? Would they? If they had exactly the same mass and they produce gravitational waves that are opposite to each other, would they cancel out? Potentially, yes. This is very cool. White holes could cause concave gravitational lensing. Yeah. So if we usually think about gravitational lensing as bending things together, whereas gravitational lensing caused by white holes would deflect things away from each other. So yeah, that's cool. But very, very cool things to think about that, again, might not necessarily be applicable to our universe. So I want to be clear here that white holes are a hypothetical concept that we are not sure if they exist within our universe. Okay, I'm just going to glance through the comments one more time to see if I missed anything. I think I covered a lot of these questions already. Oh, let's see, I covered those. Okay, there was a Lisa question that I wanted to answer as well. So I'm going to answer the Lisa question. And yes, okay. Quick fire questions. First of all, there was a question from Guada. The universe might expand faster than light in deep future in the Big Rip scenario, potentially. As we discussed today, there is no limitation. So it's quite hard to talk about the speed of expansion of the universe because you can't really define a speed to the entirety of space time. And even if you could, there is no limit on how fast space time can expand. All we know is that things traveling through space time cannot travel faster than light in a vacuum. There are no such restrictions on space time itself. Okay, question from John here that I want to answer about Lisa, and then I'll just glance at the last questions and then we'll wrap it up. Question from John: could Lisa theoretically detect supermassive black holes merging with stellar mass black holes? How about large stars? Yes. This is one of the things that LISA is actually looking for. So LISA, the Laser Interferometer Space Antenna, is a European Space Agency mission that is set to launch in about 10 years that is looking for gravitational waves. And it's going to look for gravitational waves coming from several different things. So gravitational waves, these ripples in space-time. LISA is the mission that I'm currently involved in. I'm working towards getting everything ready for the LISA data analysis, which is very cool. It's a mission I'm very invested in, of course. So LISA is looking for gravitational waves coming from supermassive black holes smashing together. It is looking for gravitational waves coming from galactic binaries smashing together. So these are all of the white dwarf binaries we expect. So white dwarfs orbiting around each other, we expect inside the Milky Way. These are also going to produce gravitational waves. LISA is looking for gravitational waves produced in the very, very, very early universe, which is what I'm working on. But another thing that LISA could detect is what is known as M-rays. And M-ray is an extreme mass ratio in spiral. This is where there's two objects where there's a massive difference between their masses, where you might have a supermassive black hole and a normal black hole. The normal black hole kind of falls into the supermassive black hole. So not so much orbiting around each other, but one merging into the other. And this is known as an M-ray, an extreme mass ratio in spiral, and this is one of the targets for LISA. So these are objects, they're called extreme mass ratio in spiral because one is so big and one is so small that instead of having the usual pattern that you'd expect, you get one really, really quickly accelerating before falling into the bigger object. So yes, LISA could theoretically detect supermassive black hole merging with stellar mass black hole or with things like that, or with massive stars. Massive stars might be a bit hard, but if you have something that's like 30 times the mass of the sun, or a black hole or a star that's 30 times the average star, and that falls into a supermassive black hole, this is something that LISA is hoping to detect. So not just theoretically, this is one of the targets of LISA, which is very, very cool. Okay, I think those were all the questions beforehand. Yes, I think we answered all of those. So let's jump to the bottom again and go through the final questions here about white holes and stuff and go from there. Comment from Breath: white holes cannot orbit black holes because positive mass attracts positive mass but repels negative mass. Yeah, so I think you could have black holes orbiting each other. We could potentially have white holes orbiting each other, but we still need to figure out how that would work with negative mass. That's the question for me to think about. That's my homework from you all. But having a black hole and a white mass orbiting each other would be difficult. A black hole and a white hole orbiting each other, would be difficult because one is attractive, one is repulsive. So it's going to be quite hard to get these to behave together and orbit each other. But it's a very cool concept to think about. Comment from John here: maybe Euclid microlensing measurements could detect a white hole or rule them out at certain scales. I'm not sure I'm not sure if the micro lensing that Euclid is going to look for would be enough to make any claims about white holes. I don't think so. But it, I'm sure people have done studies on that, on how much you can constrain these things with things like Euclid. But initially, I don't think so. There's also the thing that we don't realistically expect to find white holes. So it's not a search target for. We're not building a mission to search for white holes because we don't expect to find white holes in our universe. And we do expect to find black holes, so we're building missions to look for those. But we don't expect to find white holes, so we're not really designing a space mission to look for these things that we don't think are there. That wouldn't make sense from a building perspective. Coming from Guadav, Andromeda supermassive black hole and Milky Way supermassive black hole merging ways would be cool. Signatures would be wild. Yeah. Anytime if you have whole galaxies smashing together, which we know is what's going to happen with our galaxy and Andromeda in the future, in the very distant future, that would produce a huge amount of gravitational waves. So that would be pretty cool. Mainly if the actual well, think about galaxies, as we've established already today, space is very, very, very empty. So even though Andromeda and the Milky Way are going to collide, most objects within these galaxies will go by without feeling this collision. So then there's the question of, are the supermassive black holes at the center of the two galaxies going to pass by close enough to start orbiting around each other and eventually merge? Or will they just pass by? And I think this is not entirely clear because both galaxies are extremely empty, even when they do merge together. Yes, even when they do merge together, it doesn't necessarily mean that every object is going to merge. So a lot of the stars, a lot of the planets will not feel this. Some might be kicked out of their orbit. So the question is, are the centers of the two galaxies, are the supermassive black holes of the two galaxies going to be close enough and come into a good way where they can start orbiting and eventually crash together? If so, they will produce a huge amount of gravitational waves. If not, the galaxies might just pass by, and then you get a few gravitational waves coming from some events happening, but they wouldn't be overly traumatic. Okay, coming from Prath, I had one comment up there that you may have missed. If it's the one about, yes, S gluons and S photons, I didn't miss it, I ignored it. So I thought it was a jokey comment. So the comment was, what forces S gluons and S photons carry? So these are the supersymmetric particles of the photons and the gluons. This is supersymmetry. Is this idea of quantum gravity? Yes, supersymmetry is something that I don't talk about enough, perhaps. But yes, let me just check something about supersymmetry before I answer that. Supersymmetry, yes. So supersymmetry is the idea that you might have a mirror image of our standard model of particle physics. So everything that we know of for our standard model, there might be a mirror image of this, which we call it supersymmetric particle. So we have our own particles, and then we have the kind of symmetrical ones. And this is something that we have not found any evidence for yet. It's something that people have put a lot of work into thinking about, but it's not something we have found evidence for. But then you could have the symmetrical. So if we find supersymmetry, it could explain things like dark matter, it could explain the different masses of particles, the different forces of particles, and things like that. But we have not found any evidence for supersymmetry. But if supersymmetry exists, you would have the supersymmetric version of the gluon and the supersymmetric version of the photon. So what forces would these carry? No idea. But it's a cool question to think about. I feel like when I started my undergrad, which is 16 years ago now, or 15 and a half years ago, just let that sink in. So when I started my undergrad, it felt like supersymmetry was just around the corner. We were about to find it. We were about to discover it. The Large Hadron Collider, CERN, was going to find it, and then it didn't. And I feel like over the last few years, a supersymmetry has kind of lost general appeal that it had because we haven't found it yet. Now, of course, there's always ways you can try to save it. And there's papers sometimes saying like supersymmetry is dead, and a week later supersymmetry is not dead. But I feel like it was the main topic 15 years ago, and today it's perhaps a less explored or less pursued topic because We expected if a lot of the models of supersymmetry were expecting discoveries at the Large Hadron Collider that didn't happen. So yes, I don't talk about supersymmetry because it's not something I've worked on, but it is cool to ask the question of what would these symmetrical partners have. Now, because physicists are terrible at naming things, instead of coming up with brand new names for the supersymmetric partners, they just added an S in front of them. So the supersymmetric partner of the photon becomes the S photon, which is read as S photon and not as S photon. And the gluon is S gluon. And then that also means you get, we have tops, bottoms, charm, strange, up, down. So then you get the sup, sup. It's actually the S up, but I'm more amused at the hey, sup. You get the spottom or the S bottom, or the stop, S stop. Anyway, you can have a lot of fun with Susie, supersymmetry, but it's definitely not something that I'm going to engage in too much because I'm not an expert on the topic and I've never been a huge fan of supersymmetry. But it's a very cool topic. Okay, so homework for myself this time, both from class, is to look up quark confinement with virtual particles. Thank you for that one. And to figure out if you could have white holes orbiting each other with negative mass. I feel like these conversations are going to eventually lead to some breakthrough in science because the things I end up thinking about thanks to these streams is very, very cool. On that note, thank you everyone for your questions. It's always so fun. I'm pretty sure I've answered or at least addressed most of the questions today somewhat. And it's really fun. I always come here, what are we going to talk about today? I never know what direction we're going to go into. And it's always so fun. And the questions keep me thinking really cool topic. Like now I'm going to go think about quark confinement. I mean, not today, because I don't want to think about that on a Sunday night. But that's probably going to come up tomorrow and in the office. So that might be my coffee break conversation tomorrow. So thank you everyone for joining. This is great fun as always. I really do appreciate all of the questions, all of the comments, all of the jokes. I appreciate everyone who comes in. A couple of you recently made donations on Ko-fi. Thank you for that. There's always a link in the stream so where you can buy me a coffee just to help cover the cost of running Cup of Cosmology. To those of you who do, thank you. Really appreciate it. This last week, there were a couple of you who just randomly did donations. Thank you so much. I do appreciate it a lot. So thank you everyone for joining. This has been super, super fun. We're almost at the 90-minute mark today. The streams are getting gradually longer. I am not yet sure if there will be a stream next week because I do have plans next Sunday, and I'm not sure what time my plans end next Sunday, mainly because we haven't agreed what time they start. But because I have plans next Sunday, I'm not sure if I'll be doing a stream. Let's say maybe not, but maybe yes. So maybe we'll see. Yes, Brett, you do have a reputation now in the break room. I'm always like, so that guy had a question again. But people enjoy your questions, so we do enjoy your questions. Keep asking good questions. They're always very, very fun to answer. So yes, thank you everyone for joining. Cup of Cosmology is usually online on Sundays, 8 p.m. Central, 8 p.m. if you're in Finland, 7 p.m. if you're in Europe, 1 p.m. on the east coast of the US, 10 a.m. if you're on the west coast of the US. The cats were indeed very chill today. They were up to a bit of mischief at the beginning. Now they are both sleeping. So I have one either side of me sleeping. There's one there and one on the sofa behind the screen. Both are sleeping now. They will get zoomies again imminently, I'm sure. If they like getting zoomies at 3 a.m., but that's okay. So I'm not yet sure if Cup of Cosmology will be online next week. Maybe yes, maybe no. But I should be back at the latest 2 weeks from now. So I hope to see you all at the next stream. As always, thank you everyone for all the questions, for all the comments. This has been super, super fun. I hope to see you in the next stream. And I hope in the meantime you will take care of each other and stay curious.